I'd like to, that's my duty to introduce the members of the jury, candidate, and the scientific supervisor for the today's defense of the PhD thesis of Olga Yamilova. And I am Evgeny Antipov, full professor of Center of Energy Science and Technology, and also the head of electrochemistry department of Lomonosov Moscow State University. I got PhD degree in inorganic chemistry in 1986, Doctor of Sciences in inorganic chemistry in 1997, and totally I have H index about 50 and more than 11,000 citations. So my main field of activity is synthesis of inorganic materials with important physical properties, especially which are used like in energy storage or for energy conversion and superconductors and so on. Also, I'd like to introduce the second jury member, assistant professor of energy science and technology at Skaltech, Stanislav Fedotov. He got PhD degree in chemistry from Lomonosov Moscow State University in 2017. And he is already is lead of several projects, including the projects with MIT in the past and Russian Science Foundation. His H index is 16 and citations more than 700. He is a specialist in battery materials. And he has experience in synthesis, characterization of different kinds of materials. So he is already a principal investigator in 5 research projects and participated already in numerous research projects, including various international collaborations. The third jury member is Professor Sergei Levchenko. He's also assistant professor at Center of Energy Science and Technology at Skaltech. He got PhD in chemistry from University of Southern California in 2005. He did postdoctoral studies at University of Pennsylvania, United States, and later on he was a group leader of theory department in Fritz Haber Institute of the Max Planck Society in Germany. His H index is 30 and more than 9,000 citations. He got numerous awards. The main field of research is the investigation of materials for energy applications. First of all, it's including Abanitsa electronic structure methods, quantum chemistry, DFT, Abanitsa atomistic thermodynamics, first principles, multi-scale methods, kinetic Monte Carlo. So he's a specialist in computational design of materials, first of all, for energy applications. Let me introduce the members of the jury outside of Skaltech. And the first one is assistant professor and group leader at the University of Freiburg in Switzerland, for Professor Yavana Milic. She got PhD degree in the Department of Chemistry and Applied Biosciences of ETH Zurich in 2017. Her H index 21 and more than 2,000 citations. Her research is centered around the development of supramolecular materials for energy conversion that can respond to external stimuli and adapt to their operating conditions, with a particular focus on photovoltaics. This involves a multidisciplinary approach at the interface of chemistry, physics, material science, and engineering. towards sustainable development. She has been recognized by a number of honors and awards, such as CAS Future Leader, Green Talents Award in 2020, and Zina Karl Schindler Prize in 2021. The next jury member is Assistant Professor Ani Ng. She is Assistant Professor in Department of Electrochemical and Computer Engineering at Nazarbayev University, Kazakhstan. She received her Bachelor of Science degree in Applied Physics from the City University of Hong Kong in 2009 and PhD from the University of Hong Kong in 2014. Awarded the postdoctoral fellowship from the Hong Kong Polytechnic University for her postdoctoral research works. She was a visiting lecturer at the Department of Electronic and Information Engineering, the Hong Kong Polytechnic University in 2014. H-index is 16 and about 2,000 citations. She has been working on energy materials for emergent photovoltaics. She is interested in optoelectronics, nanomaterials, semiconductor materials, and device applications. And the last jury member is Assistant Professor Danila Saranin. He is also research scientist of the Laboratory of Advanced Solar Energy at the National University of Science and Technology, MISIS. He got PhD degree in Technical Science, MISIS 2020, and internship at the University of Texas at Dallas. His H-index is 16, and already he received more than 600 citations. The main field of research is the perovskite photovoltaics. He won a mega grant as a part of research team and co-created a laboratory for the development of alternative solar panels at MISIS University, Moscow, Russia. And now let me introduce the supervisor of the student, Professor Keith Stevenson. He was a full professor and founding director of Center for Energy Science and Technology at Caltech in 2014-2022. Also, he has been had been working as a provost at Caltech 2019-2022. Also, he was a professor at the Department of Chemistry of Lomonosov Moscow State University. He is a member of the American Chemical Society, Electrochemical Society, Society for Electroanalytical Chemistry, and the Material Research Society. He received a PhD degree at the University of Utah in 1997. He was a professor till the full professor at the University of Texas at Austin till 2015. He was the director of the Center for Nano and Molecular Science and Technology, and on the steering board for the Texas Materials Institute in 2014-2016. His H-index is 61 and more than 15,000 citations. He received even last year very important international awards, and his research interests are aimed on elucidating and controlling chemistry at solid-liquid interfaces, vital to many emerging energy storage and energy conversion technologies. And now I'd like to introduce the applicant, and Miss Olga Yamilova. She is a PhD candidate at Caltech. She got a specialist degree in chemistry at Moscow State University in 2018. She already has H-index 7 and 8 publications with more than 100 citations, and she got 6 awards at various international conferences. The research interests are in the field of perovskite photovoltaics, complex LED, halide photoactive materials, and their stability improvement. And that's all for my introductory speech, and I'd like to ask the candidate to make the presentation. Olga, not more than 40 minutes.
Can you hear me? Okay. So let me start. So my name was already named here. I'm Olga Yamilova, and I would like to present you the results of my PhD research called Revealing Electrochemical Degradation Pathways in Complex Lead Halides and Design of Stable Perovskite Solar Cells, made in Skoltech. So, I think most of you know this kind of structure, which is mostly called perovskite structure, ABX3 materials. And in area of photovoltaics, we are mostly interested in lead halide materials, where B is usually lead and X is some kind of halogen. Of course, there can be some differences in this part, and A is usually a cation organic, methylammonium from medinium. It can be also inorganic cation cesium or some other variations. So these materials demonstrated really remarkable improvements in last decade regarding the perovskite photovoltaics. The current record of efficiency, power conversion efficiency of such kind of solar cells, already 25.7% achieved in 2022. And of course, it's still not a limit. And of course, such materials demonstrate particular interest in other area of photovoltaic development, such as tandem solar cells, indoor photovoltaics, and other. But despite their promising characteristics, perovskite solar cells are still not commercialized, because for commercialization, they need to satisfy several criteria. Among them, the most important probably their efficiency, which is already quite good, stability, which is not quite good, and of course they should satisfy a low self-cost, should have good functionality and ability for large-scale processing, and of course they should be utilized. I'm more concerned about the lifetime problems, because the stability of currently existing perovskite solar cells is quite bad. It's not comparable in any way with the other photovoltaic technologies, such as silicon solar cells, which for them stability is now like 20 years, and for perovskite materials it can be not more than a couple of years probably for now. There can be a lot of different factors that influence the stability of the not only perovskite solar cell, but any kind of photovoltaic device. And some of factors like influence of oxygen in the atmosphere or moisture can be elucidated using proper, probably encapsulation techniques. But some factors are quite unavoidable, such as sunlight, elevated temperatures, and electric field. My research is more concentrated about the last point, electrochemical degradation of perovskite solar cells and perovskite materials, because this kind of factor is for now the least investigated in the literature, despite its importance, I think, because there is always a built-in electric field inside the solar cell, and absorption of photons could also lead to the photoinduced electric field inside the solar cell. If we look at some literature sources regarding this electrochemical degradation, the number is quite limited. And if there are some publications, they are more concentrated about just demonstrated the fact of electrochemical degradation, demonstrating the bad influence of electric field itself. Without deep understanding of what is going on inside the solar cell. And one more important point, if we talk about solar cells in literature, if there are some experiments, they are mostly provided in various conditions from publication to publication, different device architecture, different perovskite materials, charge transport materials, and even different conditions. For example, combination of electric field with moisture, combination of electric field with sunlight, and all other factors, which doesn't give an understanding about how electric field itself influences the stability of device. If we talk about pristine material, perovskite material itself, there are also a number of publications, very limited, and they mostly observe the fact of ion migration as presented on the slide. And another important point about such kind of publication, they usually do investigation of short time degradation process, so not more than several minutes, and thus they don't give understanding what's going on large time perspective, unfortunately. So in my work, I decided to fill these voids in knowledge and do a proper investigation of electrochemical degradation of perovskite materials and then solar cell. So I decided to divide my research to 3 steps. First step is to reveal the electrochemical degradation pathway, try to reveal this pathway for perovskite materials, probably using some model perovskite material for this purpose. After gaining some understanding of what is going on inside the material, the second step is to define the most stable perovskite material among various combination of chemical compositions, probably. And then the third part, to investigate the influence of charge transport layers, which are components of solar cell, and how they influence the electrochemical stability of the complete device. And after all 3 points, the main purpose of the whole work is to propose the design pathway for electrochemically stable perovskite solar cell. So main research objectives for this work were, first of all, detection of the perovskite material electrochemical degradation pathway. And for this purpose, we decided to choose the most commonly used in literature, one of the first investigated materials in perovskite photovoltaics, methylammonium lead iodide, which is like a model material for all perovskite photovoltaics. Then, according to the detected pathway, defining the chemical structure of the most electrochemically stable perovskite material. For this, our goal is to vary some chemical structures, chemical formulas of different materials. And then after that, comparative analysis of different just charge transport materials, and probably also try top metal electrodes to understand their impact on electrochemical stability of complete device. So first 2 steps more concentrated over pristine material, and the third part is to investigate the complete device stability. So for this purpose, we mostly use 2 types of devices. First device is called lateral. It's like having a thin film of perovskite materials, then gold electrodes evaporated on top, and we just let the small channel, not wider than probably 100 or 200 micrometers, remain for applying electric field. Electric field is usually applied to these gold contacts, and some process observed inside this channel near the cathode, anode, anode and probably in the middle somewhere. And this kind of materials we investigated with chronoamperometer measurements, atomic force microscopy, photoluminescence mapping was also made, and TOF seems probably one of the most informative methods that we used in this work. And of course, we made other kind of devices, solar cells, with a traditional configuration. We used mostly ITO on glass, which was like commercially purchased, and most of materials were not synthesized, especially charge transport materials. They were purchased. So where perovskite is placed between two charge transport materials, and we have two electrodes, top metal electrode and bottom transparent electrode ITO. And these devices were investigated by using observing changes in efficiency of solar cells from time. And TOF SIMS was also used as a most informative method in this case for such kind of devices. So I want to start from first part, which is revealing the electrochemical degradation pathway for model perovskite material, methylammonium lead iodide. First of all, what we tried to do, we actually wanted to confirm one suggestion that was made in the literature, that there is a threshold voltage. What does threshold voltage mean? It means that solar cell can sustain some kind of small voltages applied for a long time, but when we increase the voltage, there is some kind of threshold voltage. After application of this one, the solar cell starts to degrade. We decided to first of all check this assumption from the literature. We assembled the most model configuration of perovskite solar cell, which is ITO, P.PSS charge transport material, methylammonium lead iodide, Fullerene derivative PCBM60, and silver electrodes on top. We applied different kind of voltages to this kind of device, and yes, we observed this kind of behavior that applying voltage more than 1 volt led to the degradation of the device. So probably there is some kind of threshold voltage, because all voltages lower than 1 volt didn't lead to any changes in device efficiency. To understand what's going on in the material itself, we decided to make this lateral configuration of device. We applied electrical bias to gold contacts. One thing that should be noted is that all experiments regarding biasing of devices are provided in the inert atmosphere, without oxygen, without moisture, and in the dark, to avoid any combinations of various factors, to observe only the influence of electric field. And after biasing the lateral device, we observed some changes in perovskite film. For example, along the cathode, the formation of some kind of canyon can be observed on IFM microscopy and also on optical photograph, which is on optical photograph visible here, and on atomic force microscopy it's visible like here. And at the same time we can see formation of something looking like new phase, new particles along the anode on the perovskite material. So there are actually changes, and they are not the same along anode and along the cathode. So this is probably some can demonstrate some redox process, probably. To check this, we decided to make a PL mapping for device for the same lateral device biased for 24 hours already. So previous devices were biased for several hundreds hours, this for just for 24, to observe some starting changes. And yes, we observed the depletion of PL intensity, and this depletion is probably influenced by appearance of some defects along the both cathode and anode, which could confirm the appearance of some redox process. TOF-SIMS analysis allowed us to understand better what's going on inside the device. So we can see that ratio of lead towards iodine after the biasing stays almost the same. But at the same time, when we look at ammonia ratio to iodine, the strong depletion of organic cations is observed, and it's exactly at the same point where we observed this kind of canyon on atomic force microscopy. And this means that we have a destruction near the cathode of organic part. Most probably there was some kind of reduction of these organic cations, which led to volatile products that left this kind of film. But at the same time, iodine looks like it remains stable, mostly. To understand what's going on better, we decided to go back once again to solar cell and to check the same solar cell that was used in previous measurements, to check it also with TOF-SIMS. And we observed very interesting point that after biasing for 300 hours inside the solar cell, the methyl ammonia cations penetrate into both charge transport layers, into both PCBM and PDOT-PSS. And if appearance of this kind of cations in PCBM can be explained by simple ion migration, because PCBM is on the cathode part, then the introduction of methyl penetration into PDOT-PSS can be explained only by the fact that we have some products of electrochemical reduction of methyl ammonia cations, which react chemically with probably polystyrene sulfonic acid, which is the component of PDOT-PSS material. Thus, after all these measurements, we were able to propose the pathway for electrochemical degradation of pristine, only for pristine, not in perovskite solar cell, for pristine methyl ammonium lead iodide material, which includes reduction of organic cation on the anode with the formation of volatile products mostly, which leave the film and thus make the whole process probably irreversible. At the same time, at the anode, we most likely have a oxidation of iodine anions into molecular iodine. But if we believe the TOF-SIMS measurement, this iodine mostly remains in the film, probably in some form of polyodides, which stays trapped in the film, most likely. And this also can be probably the new particles that we observed on AFM microscopy along the anode also confirm this suggestion. So the main conclusion made from this is that actually the major part responsible for the complete degradation of the device is a reduction process of organic part, which leads to some volatile products that live in the film. And if we somehow try to capture these kind of products and remain them closed in the closed volume, then probably we can try to make the process reversible, or to at least stay in some just a second, in some form of balance, yes. So thus we decided to go to the second part and try to define the most electrochemically stable perovskite material. So after revealing the mechanism, try to understand what kind of material would be better for a working device. And for this purpose, we have chosen several kind of materials with different chemical compositions. So here we see our traditional methyl ammonium lead iodide, fully inorganic cesium lead iodine bromine, also some methyl ammonium free materials, and materials with multi-cation structure, multi-anion structure. Of course, first of all, we made the same lateral devices, and applied electric bias. And first of all, we decided to observe the change of the current in the channel while applying this electric bias to gold electrodes. And we can see that all materials demonstrate similar behavior. So at the first times of bias applying, the current is increasing, but after some point, different for every material, the current starts to decrease. This can be explained by simple process that during the biasing we have some probably ion migration, charge migration that leads to the formation of defects. And at first, at the beginning of the process, these defects, they serve like electrochemical doping, and this doping leads to the improvement of the current in the channel. But after some point, the concentration of these defects becomes so large and so high that they don't work as a dopants anymore. They work like they start like the degradation process itself, and then the current starts decreasing. So in this kind of suggestion, it's probably correct to assume that if we try to measure the area beneath the part when the current is increasing, we will be able to at least make an assumption which material can sustain the most amount of these kind of defects accumulating inside of it. And according to this assumption, the most promising material out of these 5 is cesium, is the first one, cesium formidinium lead iodide. And the worst one is fully inorganic cesium lead iodine bromine. PL mapping also confirmed our suggestion. Here you can see that during the biasing of the device, during the first probably first hour at the beginning of the process, the PL intensity is increasing, which also correlates with the with information that current is increasing during the beginning. And then we have a depletion of PL intensity, especially along the cathode, along the negative electrode, yes. And even after biasing, after 120 hours, and yes, after 120 hours, it's also can be visible just on simple photos of the devices that the material between the two gold cathodes is completely ruined, unfortunately, except for one, the most stable material, cesium formidinium lead iodide, which demonstrates much better performance, up to 400 hours, and almost no visible changes on photographs. We also decided to provide TOF SIMS measurements for those materials, and you can see that methylammonium containing perovskites all demonstrate the strong depletion of organic part along the cathode. So we already discussed this for methylammonium lead iodide, and here you can see multi-cation structure methylammonium cesium formidinium lead iodide, also strong depletion of organic cations. If we look at methylammonium-free materials, the situation is mostly better for them, especially for, once again, cesium formidinium lead iodide, which demonstrates the best performance for now in all current experiments. So the depletion is, of course, still present of organic part, but it's not so strong. And regarding all the other points, I would like to say that TOF SIMS analysis, especially for perovskite thin films, is quite tricky. So it's very difficult to understand what's going on. It's only possible for comparative analysis, I would like to say. So we also decided to check the atomic force microscopy for this kind of film, and you can see here once again for methylammonium lead iodide the formation of canyon along the cathode, strong degradation of the material. And for cesium-formidinium lead iodide, which demonstrated the best performance in previous experiments, there is also, but much less formation of some kind of canyon. And you can also see that on top of gold electrode, on the anode, on the top of gold anode, formation of some new species, probably it's a reaction of gold with molecular iodine and formation of gold iodide, most likely according to the form and conditions. And also at this stage, as far as cesium-formidinium lead iodide demonstrated the best performance, we also decided to try its improved chemically improved materials like cesium-formidinium lead iodide with small excess of lead iodide initially, and also decided to check rubidium containing cesium-formidinium lead iodide, where part of cesium is replaced with rubidium. These kind of materials were reported in the literature, demonstrated quite good stability improvement in terms of photodegradation. And so we decided to try them also. And according to the atomic force microscopy, cesium-formidinium lead iodide with excess of lithium iodide demonstrate no changes along the both cathode and anode in terms of morphology. So this material and the same behavior was for rubidium cesium-formidinium material. So we decided to check all of our materials also in completed perovskite solar cell and compare them. And as it was comparable with atomic force microscopy, the best materials was cesium-formidinium lead iodide with the excess of lead iodide. So probably the excess of this lead iodide shifts the balance in the perovskite material degradation towards the initial perovskite structure from the degradation products, as it was observed for photo degradation experiments by our colleagues and by different researchers. So the second plates belong to rubidium-containing perovskite, and unfortunately, the bottom, as is probably was expected, was for inorganic material and methylammonium-containing materials also. So as far as we understood what kind of material is the best for our stable perovskite solar cell, it's time to shift to investigating of device and how its configuration influence the electrochemical stability of solar cell. So according to research of our colleagues, the adjacent charge transport layers are very important for the whole material stability because they can probably chemically interact with perovskite material. They can serve as a as a starting point for some defects, for defect degradation and all this kind of thing. So we also decided to check different kinds of whole transport materials, like the most common materials like polymeric, PTA, PDOT-PSS, which is consists of two components. Also such salts as copper iodide and oxides like nickel oxide. I would like to point that here you can see that they are written like copper OX and nickel OX, and this represents that we have some kind of difficult mixture of different oxides. So for example, for copper oxide, we have a mixture of copper 2 plus and copper 1 plus oxide. And for nickel oxide, we have nanoparticles, which are also of very difficult composition, and thus it's established in the literature to call them, to write them with the letter X. So first of all, we decided to try accelerated experiment, which is called stepwise biasing, when we applied different biases to our devices and stepwisely increased it up to 2.2 volts. And you can see that all devices start to degrade at different applied voltages, which is also confirms our previous observation that we have some kind of threshold voltage in the devices. And thus the question arose that we should choose the proper biasing voltage for all further experiments. So we provided these experiments for PTA HTL solar cells. And according to this experiment, we decided to choose the voltage 1 volt, which is close to open circuit voltage of this kind of devices, PTA devices, and actually close to all other kind of devices. So we check huge amount of different whole transport materials and also their combinations to probably check how introduction of polymeric PTA between perovskite and oxides and salts can influence the degradation of material. And according to this table, which represents the rating of perovskite solar cells with the various whole transport materials, the bottom of the rating belongs to materials which consist aggressive factors like P.PSS, which includes acidic polystyrene sulfonic acid, nickel oxide, which is first of all water processed, and then it also can include OH minus in its structure, copper oxide, and then go copper salts, which can be probably partially flushed by perovskite solvents. It's not confirmed, but still it's sometimes observed in the literature. It's just an assumption. And you can see that the top of the rating belongs to the whole transport layers, where actually PTA polymeric fully chemically inert towards perovskite material with toluene, which is also completely inert towards perovskite solvent, and those materials not flushed by perovskite solvents also. And if you look also at the top of the rating, you can see that here the higher the open circuit voltage of the device, the higher the stability, and also the higher the maximum power point for the device, higher the stability. So we can make a conclusion that for stable perovskite solar cell, we first of all need charged transport materials that chemically inert over perovskite, that won't be flashed partially by perovskite solvents, and which will give us the best starting characteristics, meaning especially open circuit voltage for the device. We also decided to check several electron transport materials, like several oxides, and also introduced C60 and fullerene derivative PCBA between oxide and perovskite. You don't see any data for pure perovskites on this graph, because this kind of materials led to the complete destruction of solar cell just in several minutes. So it was impossible to include them in this graph. But among these kind of materials, the best was tin oxide with introduced PCBA between it and perovskite. So we can assume that PCBA works the same as PTA in previous experiment. It's like a barrier between aggressive oxide and perovskite material. Of course, ideally, it would be probably better to introduce some kind of polymer between electron transport oxide and perovskite, but unfortunately, obtaining electron transport polymer is quite a tricky task, and for us, it was unfortunately impossible. So we also, since in all our previous experiment, we tested solar cells with silver electrodes, we also decided what will happen, decided to ask ourselves what will happen if we try other materials. like gold, aluminum. Aluminum is quite really traditional also, and gold and different other materials, actually all what was available for us. And we found out that the most stable solar cells would be actually not with the gold, not with the silver electrode, and actually for gold and aluminum electrodes. One of the reasons why is it happened so can be demonstrated on this TOFSIMS analysis of nickel oxide PTA solar cells, which demonstrates also why PTA is important and what's happening on the electrode side. So you can see that when we have pure nickel oxide as whole transport material, we can observe the complete destruction of perovskite layer. For example, in the red frame, you can see that all organic part, like formidinium cation, it's actually is not on its rightful place. After the degradation, it's like almost all of it is concentrated in the fluorine derivative part. And also you can see in the green frame that silver plus is quite brightened after the degradation, and exactly at the same level you can observe the iodine anions, which is like a purple frame, and we can assume that after the biasing we have migration of iodine ions towards silver electrode and corrosion of silver electrodes because it's very reactive towards iodine. And you can also observe on these microscopic photos on the bottom that a fresh device, which was like really beautiful and smooth, after the biasing for nickel oxide material became rather rough and bad quality and with a lot of pinholes actually also. And if we look at the nickel oxide PTA device, we first of all observe actually no such drastic changes as for pure nickel oxide material, only slight intercalation of various ions into neighboring layers. And if we look at the electrode, it remains, the changes are also not so drastic. And if we look at the photos of the backside of the electrode for nickel oxide, you can see, especially at the edges of the electrode, the corrosion starts significantly. And after some time, this corrosion also will spread all over the device. So it usually starts from edges and then spreads everywhere. So according to everything was mentioned here, we can make several conclusions, like electrochemical degradation. We proposed the electrochemical degradation pathway for hybrid perovskites, and we think that applied electric bias induces the redox reaction, which includes oxidation of iodine anions into molecular iodine and reduction of organic methylammonium cation in this case, and producing volatile products. The influence of chemical structure, of chemical composition on electrochemical stability of bulk material and complete device was demonstrated. And we made a conclusion that replacement of highly volatile methylammonium is with the bigger cation like formidinium or even inorganic cations like cesium or even rubidium improves the stability of the device. And actually addition of some excess of lead iodide, which is like one of the products of degradation, could also lead to some positive changes. And a general pathway for electrochemical degradation of solar cell, we also propose this kind of pathway that small bias in voltage and duration can lead to the electrochemical doping and efficiency increasing. Especially it was observed for PTA devices which were biased for with the voltage equivalent to the maximum power point voltage. And further biasing or biasing at larger voltage induces can induce interlayer ion migration and even aggressive redox process if we have some kind of factor that comes from adjacent charge transport layers. So most likely, if we don't have aggressive factors, the only result will be slight interlayer ion migration. But when we have such an aggressive layers, components, charge transport materials, the redox process in the solar cell is inevitable, unfortunately. So we also provided the first systematic study on the influence of different charge transport materials on the field-induced degradation of solar cells, and we can imply the most important factors for improving the solar cell is try to provide solar cell with as much higher open circuit voltage or with as much higher maximum power point voltage device as possible. Another important factor is chemical inertness of adjust charge transport materials and their solvents towards perovskite, and of course insolubility of charge transport materials in perovskite solvents, so they won't be partially flushed away, and of course formation of tight flawless film as it was probably for PTA material, which formed polymer, which was polymeric. And of course, another important factor is the low reactivity of top metal electrode to iodine to avoid such kind of effect that we observed for on TOF SIMS results. So I think that's all I wanted to say. The results of this work were presented in 3 already published papers, and 1 is submitted for now. Also, the results were presented on 6 international conferences. Some of them received prizes. And I also would like to thank all colleagues that helped me with experiments, especially with AFM experiments. Dr. Sergei Luchkin from Skaltech. TOF SIMS measurements were performed by our colleagues from Institute of Solid State Physics of Russian Academy of Science, and also with our colleagues from Skoltech. I also would like to thank my scientific advisor, Professor Keith Stevenson, members of my individual committee, and of course, all my colleagues and my family for their advices and for their support. Thank you very much.
Thank you very much. And now, the next part of the defense, that each member of the jury can ask questions, new questions arising from this presentation. And what is important, that each jury member should say either he or she is confirmed or not, he or she is satisfied or not with the changes which were introduced in the thesis after the review of the thesis, because the applicant had at least 1 month to introduce the required changes in the thesis. And now I'd like to ask Professor Levchenko firstly to start and to ask any questions and to say either he is satisfied or not with the changes. Please, Sergey.
Thank you, Evgeny. Thank you, Olga, for a very nice presentation. I think thesis is very clearly written, and because many different methods were used to show different aspects of this problem, I think it's very convincing. So that's my impression. I'm satisfied with the changes, so everything was fixed. I have just one question. I think on slide 24, I don't know if we are supposed to see the slides. It's just more convenient to look at the slides. Slide 24. Yes. So here, okay. Yes. So here in particular, and in principle, it's a general question. I see that, for example, cesium Fa lead iodide, the first one with 0.12%, and the next one with 0.15%. So it's the same material with different concentrations, but it has very different properties, right? These two materials. Can you explain why? And in general, can you think or suggest what will happen if you change this concentration? Do you find some optimal concentration, or how does it work?
Thank you for this question. Actually, these two materials, which are really separated in this rating, they have a very drastic change in their chemical composition, because as you can see, the bottom one, cesium 0.15, then fermidinium 0.85, lead iodine 3, it's a completely stoichiometric material. Which fully corresponds to the formula ABX3. And if we look at the top one, it's cesium 0.12, fermidinium 0.8, and then lead iodide 2.92. This material, it's it's not non-stoichiometric, but there is some excess of lead iodine compared to all other components. So probably why we used this kind of material, because it was tested by our colleagues in some different publication. It was confirmed that this kind of addition of excess of lead iodide, not only in this kind of material, also same results were confirmed if we add some excess of lead iodide into methylammonium lead iodine, some other materials. This kind of excess can improve the stability of the material itself, the stability of the solar cell where the material is used. Because probably when we see this kind of, probably you remember on previous slide the mechanism, we have at the left the perovskite, and at the right side, when for every reaction, initial components and products. And one of the products of every perovskite degradation, one of the most products for this degradation, is actually lead iodide. And probably the addition of this excess of lead iodide initially shifts the balance between these two sides of the reaction to the initial components point. So, and if we talk about finding the better composition for improving the degradation, in this work we, just to save time and save our reports, mostly used materials that were already in literature mostly, and they were confirmed to have quite good results regarding the efficiency, regarding their structure, phase purity, and regarding their stability. But in most of the cases, they were investigated for photo-induced degradation, and we decided to check them also in case for electrochemical degradation. Of course, the even slight changes in perovskite composition could lead to very different experiments. I saw on one of the conferences, I haven't seen the publication about this yet, but on one of the conference, one presenter demonstrated that they somehow took probably methylammonium lead iodide and tried to change the composition just with 0.01, by adding just 1% of excess of some kind of component, and the stability, the efficiency of the device drastically changed just from these small additions. So it's quite a tough task, and actually finding the exact best composition of perovskite material is a task for everyone who working on the perovskite solar cell, and that's why every year we have different kind of compositions proposed by different authors, and of course all this kind of composition very interesting, but still they can be also quite tricky, actually, because some composition are quite sensitive to their adjacent layers and all this kind of stuff.
Oh, okay, I see. Yes, it's clear. Just to clarify a bit more. So you do not expect that this change is due to the composition and cesium concentration, but you expect that if you create excess of lead iodide, you would get about the same in both, right? If you create in the second one, cesium 0.15, create this excess of lead iodide, you would get about the same
Probably,
stability.
yes. Probably if we add some excess of lead iodide into the into the stoichiometric structure, it could be, there could be some improvements, but at the same time, it should be made quite carefully because we can lose the purity of the phase. So it's, for example, this top configuration of cesium 0.12 was, yes, it started, it was a deviation of this bottoms configuration made by our colleagues. So they took this stoichiometric material as basis and tried to add some excess of lead iodide. But in order to remain the cubic phase pure, we needed to somehow adjust and other components of this material, and this led to this kind of chemical formula.
Yes.
Yeah, I'd like to interrupt Sergey and to ask you, continue on that discussion. I look on Appendix A. Can you show, Appendix A on the screen? Is possible or not? And I'm looking on X-ray diffraction pattern for cesium 0.15 and cesium 0.12. Yeah, these two compounds. So you said this is a cubic symmetry, yeah? That's correct or not?
For perovskite photovoltaics, we're mostly interested, yes, not exactly in cubic symmetry, but in alpha phase. So I would not say that it's...
Olga, you presented X-ray powder diffraction pattern.
Yes.
So you said you compare with literature.
Yes.
Therefore, you should provide indices and to say what is the symmetry. But I found that cesium 0.15 and cesium 0.12, the second phase or the second pattern is indeed a mixture of phases, while the first one is a pure single phase. You can just first comparison. Yeah, I'm not a specialist in such type of perovskites, but all my theses, including Doctor of Sciences, were devoted to the perovskite structures. And therefore, my impression that D pattern correspond of mixture of phases, and this mixture of phases represent the best stability. Can you to say either I am right or I'm not right? How you prove that this is a single phase?
If I remember correctly, the figure D, which we refer to, is also representing the single phase, but all these additional peaks, they actually go from the substrate that we used for the measurement.
Yeah, but why you did not show that this is substrate peaks?
Yes, that's my mistake, probably. But what was the main point for showing this Appendix A? Actually, the purity of phase is mostly confirmed by this major peak, which occurs near the 15 to theta degrees.
Yeah, but you did a very small deviation from the composition, yeah?
Yes.
Small deficiency. For this composition, it should be anion deficient perovskite. Yeah, with some deficiency in anion sublattice.
Yes.
In some cases, it's possible. For instance, a lot of so-called anion deficient perovskites. In your case, I compare the C and D. I see that the major peaks, okay, they're similar, but the peak around 32 degrees to theta, it's a new one. You said this is a substrate. You checked it that this is a substrate.
Yes, as far as I remember, it's a substrate. It can also be visible on figure B. Yes,
No.
on figure E. So this kind of peak, they can be visible on several graphs, and they all represent the substrate.
And why there is no on C?
It depends actually from the crystallinity probably of the film. If the film has a high crystallinity, the whole intensity of XRD is quite high, and then this substrate peaks, they have small intensity and they're like noise in the bottom. And if the crystallinity is not so high for the material, the whole figure becomes quite noisy, as you can see for some, for example, H, F, and all others, and then the substrate peaks can be visible actually.
Okay, what is the Miller indices of the first peak on C?
I'm sorry, I'm not sure about this kind of, how to say, I'm not a specialist in XRD data. I mostly use it in order to confirm the purity of my face and how my materials correspond to the literature. I usually not proficient with strong kind of analysis of XRD data.
Okay, Sergey, please continue.
Okay, yes. So one last question. What about like absolute PC power conversion efficiency for these two materials? How they compare?
For these two materials, it was quite similar, I would like to say. I actually tried to adjust to get the most possible efficiency from every kind of material. And these two materials, they were both in the area around 16% if we talk about absolute efficiency. So it was quite similar. The only difference is stability, probably difference.
Mm-hmm. Okay, thank you. Everything is clear.
Okay, and now I'd like to present the report and comments of Professor Fedotov. Unfortunately, he cannot participate today in the defense due to the serious personal reasons. And first of all, his report is very positive, and you can read it. I just will read the main conclusion that he did a lot of comments concerning the orthography, mainly in the text, language editing, and asked a few minor scientific questions. However, these commentaries do not underrate the high quality of the work, and Stanislav Fedotov said that the candidate should defend this thesis by means of formal thesis defense. And also, after presenting the answers on the reviewer comments by Olga Yamilova, he wrote me that he's fully satisfied by all changes which were made in the thesis, and he has no any other questions. So in the log file there are the answers of Olga's on questions of Stanislav Fedotov. I will not read them. They are not so essential to estimate the quality really of the presented work. So that's all about the Professor Stanislav Fedotov. his participation as the jury member. And now I'd like to ask the next jury member from abroad. I'm looking at Yavana Milic, Professor Yavana Milic, to either to ask you can ask her any questions which arise after that presentation, and importantly, you have to say either you are satisfied, Giovanna, or not with the changes made in the thesis, please.
Well, thank you very much for the introduction and opening the discussion. I hope that you can hear me well.
Yes, we can.
Very good.
Yeah, we can.
Wonderful. Thank you. Well, thank you very much, Olga, for an excellent presentation, and also the thesis. I very much enjoyed both the presentation and reading and evaluating the thesis. From my perspective, regarding some of the critical remarks that I made in my evaluation, I can confidently say that they all seem to be appropriately addressed. So I do not have further remarks regarding these critical points that are raised. So thank you for addressing them in detail. I do have a few questions that partially relate to this, but that are also further stimulated by the presentation that you had, as I would like to hear more from you in this regard. So the first question that I have, in fact, refers to your chapter 2 and the assessment of different compositions and their stabilities or instabilities. So the role, and this particularly the role of this excess lead iodide, that is not something unusual in the research community, and that is commonly used, and which you nicely assess then in the context of different compositions. But can you comment perhaps what was your rationale originally on using this in one of your compositions, and in particular one specific composition with two different cations? What was your rationale for using this excess lead iodide when assessing these stabilities?
If I understood correctly, your question is why I first of all decided to try this cesium from medium lead iodide with excess of lead iodide.
That's
yes?
correct. So can you comment? Of course, you explained very well what your conclusions are, how this affects the resulting stability, but I'm curious, when you have decided on these compositions, what was the rationale behind using the excess?
So the reason I tried all of this material, not actually only this one, all of this material I used because by the literature data, by the results of my colleagues from their experiments on photo-induced degradation, thermal degradation, these kind of materials, all of them, not only this material with excess of lead iodide, demonstrated better stability than probably other materials they were compared with. Especially with this material with excess of lead iodide. If I remember, it was like one of the foundings of one of my colleagues who actually now works abroad of Skoltech. But still, this person firstly tried this composition for photo-induced degradation of perovskite solar cell, and he was quite surprised with the outcome. And so another my colleague also tried perovskite with rubidium, with replacement of cesium with rubidium, and he also got quite interesting results regarding photo-induced degradation. And so looking at their results, at their conclusion towards why is it happening, I also decided to try these kind of materials in my work, and probably that's one of the reasons why they appear in the middle of the second part, not exactly at the beginning, because I first of all started with just limited number of 5 materials, but at some point I also thought about if the fully stoichiometric cesium formidinium lead iodides demonstrates the best results from all these guys, all these 5 materials I investigate, and my colleagues get even more interesting results with this improved material, which are quite similar to this cesium fermidinium, but still improved in terms of chemical composition. Why can't I also try them? Will it be able for me, in terms of electrochemical degradation, also get some interesting results?
Very good. Well, thank you for clarifying this. I wonder now, so I see now that the compositional choice has been really guided by these empirical insights moving forward. Now, having assessed this system, can you summarize what are some of the perhaps chemical reasons or origins of these now observations of your stability changes in presence of excess lead iodide? What can you summarize your main conclusion when using the excess lead iodide, and what are the reasons behind?
Okay, first of all, according to the first part, the major problem of all this electrochemical degradation process is the reduction of organic cation, yes, and formation of some volatile products. And the first conclusion, if to try somehow go to exclude methylammonium from the chemical composition, which was actually demonstrated that our methylammonium-free materials demonstrate quite better stability than others. So it was about choosing formidinium, which is a much higher, much larger than methylammonium.
If I may interrupt you here for a moment. So what I'm mainly interested in is in the role of this excess lead iodide. And since all of them are primarily focused on formamidinium cesium compositions, can you maybe just comment on the chemical reasons behind just the excess of the lead iodide?
Just the excess, yes, as I already mentioned. If we look at the reaction, in major of cases regarding the decomposition of any kind of perovskite, one of the main products of degradation will be lead iodide, which can further, of course, go into pure lead and all other kind of stuff. So probably the introduction of additional lead iodide at the beginning in the initial material will probably shift this degradational reaction to the initial, not to the products, but backwards to the initial components. This is one of the major assumptions, probably. And of course,
so you argue that this equilibrium shift is the major reason for the issue. If I may just ask a follow-up on this, do you see any evidence of structural changes or coexistence of other phases, so other than lead iodide, in presence of this excess lead iodide?
No, I haven't seen any deviations. So the phase was quite pure. So I haven't seen any problem. If there were too much lead iodide, it could be visible on XRD measurements, probably as a separate peak. But since there were absolutely no separate peaks for lead iodide, I assume it's like introduced into the perovskite lattice quite well. Despite its excess, so the phase was quite good. Probably it also influenced somehow the stability of the device, because as far as I know, it refers to any kind of perovskite material. The better the crystallization, better the phase stability, also the whole stability of the material would be better. Actually, that's also they can be a superposition of all improvements that excess of lead iodide brings to this material, actually, not only the shifting of the equilibrium.
I see. So you argue that there is a complexity of or an interplay of different factors. I'm curious now about what you said, that even though there is an excess, you don't really see it in your XRD patterns. What could be the reason for that? You argue that it's incorporated somehow, but if that's the case, you will be seeing additional phases, isn't that?
Probably yes, but the concentration of this lead iodide excess is not so large, I think, to see it like a separate phase on XRD compared to the whole perovskite intensity. Probably. If the excess would be much larger, of course, we could see the just additional phases on the XRD pattern, but still, so the introduction of additional components should be in moderation, as I think, because there too much excess of lead iodide could lead to the destruction of perovskite lattice, probably in most of the cases, and there are some examples like that.
Okay, thank you for answering that. Can you maybe comment on what could be another reason of not seeing this excess lead iodide?
I'm sorry, reason for what? For what do you mean?
Not seeing it in your, or not
seeing
this phase in your XRD patterns.
For example,
even if it's present,
it's
one of the reasons you argue being is the
probably one of the reasons
concentration, if I understood well.
First is the concentration, and second, if most of this excessive lead iodide is concentrated on grain boundaries, probably. Not in the form of crystal lattice. So XRD mostly sees the crystal. It gives better results if the material is in the form of a crystal, as far as I understand. If our lead iodide is in the form just like amorphous, is in amorphous phase, it could be less visible, and in amorphous phase it could also be on the grain boundaries of perovskite material, most likely, something like this.
Indeed, I agree with you that should it be in the amorphous phase, you will not be able to visualize it even if it's there. So very good. Thank you for clarifying all these details based on this question. I have just two brief follow-up questions, if that's still all right with respect to the time. One of them refers to now the assessment of the role of the device architecture in combination with specifically identified more stable perovskite compositions. Now, based on everything you assessed, can you tell us what would be the most appropriate architecture overall for reaching the most stable solar cell architectures at the moment? What is the architecture that you would recommend?
Okay, first of all, actually, I would recommend probably PIN architecture, in my point of view, because the PIN architecture provides devices with less this effect on perovskite photovoltaic hysteresis, yes, with less hysteresis. And hysteresis, which is actually quite, how to say, tricky parameter, tricky property of perovskite solar cells, which is widely discussed in literature, but still uncertain. It could also lead to some additional problems with device stability. So I, first of all, would recommend NAP configuration and choosing this, the most stable perovskite material, and adjacent layers, both electron and hole transport, in my opinion, should be the best are like polymeric, especially polymeric like PTA material, which are chemically inert to perovskite material, polymers, which are processed with such solvents as toluene, probably, which are quite used like anti-solvents for perovskite, so they don't dissolve perovskite, and these polymers also shouldn't be dissolved by perovskite solvents like dipropyl sulfide, dimethylformamide. So polymerics are the best, but I understand that getting polymeric electron transport layer is a very tough question, and it should be properly addressed. So probably as an alternative, like small molecules, but they would work, I think, much worse than polymers still, because they don't form such a good quality film. Probably one of the positive properties of polymer that they form a good quality film, which doesn't allow any products of perovskite degradation leave the perovskite film, the area where perovskite should be concentrated, all stuff like this. And according to the my knowledge about electrodes, if we talk about metal electrode, the best will be gold or aluminum. And I haven't tried such interesting electrodes as carbon electrodes, carbon nanotubes, or even transparent electrodes on top. So this requires, in my opinion, additional probably experiments using this kind of non-metal electrodes, and this could lead also to some interesting results. As far as I know for now, the best solar cells in perovskite, in all perovskites regarding stability, for now use carbon electrodes. So probably they would be the best also for electrochemical stability.
Thank you very much for summarizing this. Excuse me for a very brief kind of camera issue interruption that interfered a bit with the audio. So the only aspect that I didn't fully grasp when you analyzed or you summarized all your results in your ideal architecture for perovskite solar cell stability was actually the electron transport layer. Can you restate just this? You said that you recommend polymeric charge transport layers, and you explained that you would focus on PDA, particularly toluene process. But then I had an interruption in my connection, unfortunately. What would be your ideal electron transport material?
Yes, the best is polymeric, but I understand that getting polymeric electron transport layer is difficult. Very difficult. And so probably the alternative could be small molecules electron transport layer, but they still won't be as ideal as polymeric because they can't form a good quality film which won't let any perovskite degradation products leave the perovskite film. So between small molecules, there can be still some voids, probably, just because they are separated.
Well, thank you very much for summarizing this. I think this captures a lot of your findings throughout the thesis, and I'm glad to hear this comprehensive summary. Now, looking a step beyond this, what is your view on the perspective of these compositions in perovskite solar cell applications and their stability under more real-world conditions? Do you believe that they do have a future in this direction?
I believe that they do have a future, but not in the area where we use our current photovoltaics for now. For example, they will never be, in my opinion, they won't be competitors for silicon batteries. So I don't think they will work, and they will have so much stability to work like in the large fields, in the large photovoltaic energy bases, this kind of stuff, because there will be too much of sunlight, too much of heat up of the devices, and all this kind of stuff. In my opinion, perovskite solar cells will most likely fill the area of indoor photovoltaics, because this area will still, I think, will be developed somehow. And the whole area of smart homes and all this kind of stuff is developing really rapidly and requires a lot of different kind of energy. Not different kind, but requires a lot of energy. And another possible implementation for perovskite materials, in my opinion, is in tandems. Most likely, because there we will be able to try somehow and protect perovskite layers from aggressive, for example, ultraviolet light by other additional layers, additional solar cells which are placed on top, and all this kind of stuff. So not in terms of traditional photovoltaics as we imagine it in our minds, but perovskite photovoltaics still have a lot of opportunity in this kind of places, like indoor and tandems, in my opinion.
Well, thank you very much for also engaging in this more forward-looking perspective based on all of the research you've done throughout your thesis. So this answers all of my questions at the moment. Thank you once more, and congratulations on a successful research that is conducted in this thesis. And I don't want to take more time from my other colleagues, but I look forward to the continuation of this discussion. Thank you.
Thank you very much.
Thank you very much, Joanna. And now I'd like Professor Ani Ng from Nazarbayev University to ask any questions if they appear, and of course to say either you are confirmed or not with the changes, please.
First, thank you very much for very impressive presentations, very comprehensive. So the student have addressed my concern properly in her thesis already. But now I have some other minor issues I would like to clarify after her presentations. The first question is still about the most optimized recipe. Surprisingly, appear to be like excessive lead iodide. Yeah. My question is, how do we confirm the final recipe of this particular optimized perovskite with cesium 0.12, from a medium 0.8, and lead iodide. For lead iodide, the iodide composition is 2.92, which is a very precise value. More than that, the XRD cannot show the additional excessive lead iodide peak. And maybe the student can comment, is there any color characterization can help to verify the exact optimized composition of the perovskite?
Yes, thank you for a question. Of course, in my work, these chemical formulas for perovskite materials, they mostly represent how these materials are named in literature, first of all, and second, they mostly represent the initial ratios of substances that were mixed in the solutions when we took just lead iodide separately from medium iodide separately and all this kind of stuff. So, and my goal was to just repeat the recipe from the literature and confirm the purity of phase. And according to what's usually done in all this perovskite area, usually this is enough. And of course, if we talk about precise chemical composition, the additional measurements should be done to know the precise up to 3 numbers from yes, up to 3 numbers should be known. And with this, some additional methods like EDX could help. I haven't done it just because my main goal was to reproduce the literature recipes with different composition. And still, since our my materials, like during the preparation, they were completely soluble, they completely dissolved in their solvents, we assume that their resulting composition is most likely the same as it probably written, and if there are some deviations, they are not so drastic, not so significant. So we didn't have any precipitate. We assume that all our initial ratios of components dissolved completely and formed exactly desired material. Of course, if we want to know the exact composition, the additional measurements like EDX should be done, in my opinion. But actually, this mostly done in the works which are actually concerned about the chemical composition, which investigated some kind of new material. So they, if these publications provide some new recipe, they should confirm their material with several kinds of methods. And after they confirm this kind of material, they wrote the the other publication are able to repeat them according to their recipe, and in most of the cases they confirm just the purity of phase and how this XRD pattern is corresponding to this first initial publication in most of the cases, and for me too.
Okay, so in my opinion, since the reason for explaining the result is due to the excessive lead iodide, partially at least. So in order to make the conclusion stronger, the first thing is to confirm our hypothesis is correct. So in my opinion, it is important to claim the excessive lead iodide containing perovskite behave more stable than other types. So this is my personal opinion, and we'll see if there will be other literatures you can cite in your thesis to make it, your point make it stronger. But meanwhile, I also read some of the publications indicate that the presence of the lead iodide, excessive lead iodide in the perovskite will cause faster degradations. So since you are working on this type of materials, can you comment why there is a discrepancy of the result between your work and the literatures?
Yes, thank you also for this question. And as I already mentioned during answering questions, I once saw the presentation at one conference of one lady who made exactly a very interesting investigation. I haven't seen the publication yet, probably it will be soon. So what they tried to do, they tried to make an excess of various components of, for example, methylammonium lead iodide, and they tried to add some different amounts of excess of lead iodide or some excess of methylammonium iodide. And they could observe that probably if you add just less than 1% of excess of lead iodide, the stability is increased, the efficiency is increased, and so on. But while you increasing this amount of excess of lead iodide, at some point, all the efficiency and stability will just drop down significantly just by adding one more additional, I don't know, 0.1% of excess. So probably such kind of large difference between my results and some publication can be connected with the how much of excess do I and they add into the into the perovskite and all this kind of stuff. So it all should be also discussed, maybe.
It is highly possible. Thank you very much. And my second question is about still stability. Yeah, so actually the perovskite is sensitive not only to electrical chemical direction, but also thermal stability, as well as the for example, moisture, for example. Yeah, I understood that your thesis direction is electrical chemical reactions or degradations. However, when you design your experiment conditions, have you considered the degradation behavior can be due to the moisture or can be due to the ambient light, for example? So the cesium-based or inorganic perovskite, for example, in your result seems not very stable compared to the first one, the recipe with lead iodide in excess. However, maybe the degradation is not because of the electrochemical stability, can be due to other factors such as moisture or the temperatures or other factors. So how do you exclude other factors to make the final conclusions?
Actually, why I exclude the moisture, oxygen, ambient light is just because all experiments, except for PL mapping, all experiments were provided in the glove box. in the closed glove box in the dark, so with no additional heating up of the atmosphere. And I mean, all the measurements like efficiency of the device from time, chronoamperometric, even atomic force microscopy was done in the glove box. So the influence of moisture, sunlight, and oxygen can be excluded. The only point when our devices could meet the ambient atmosphere probably was the measurement of PL mapping, just because this device is placed outside of the glove box, because it's quite a big device. But still, before the carrying devices out of the glove box, I encapsulated them with several types of encapsulator films. One of them was Eva traditional, and to another I'm not sure how they called. They have a difficult name from the store when they were bought. But still, some materials degraded rapidly, even in such only electrochemical conditions.
Mm-hmm. Okay, thank you. And then I have another suggestions. Okay, you may consider in your thesis, which is about the power conversion efficiency (PCE). I understood that the aims of your work is to compare the lifetime, so that you just need to normalize the efficiency to 1, and then compare the difference among the samples. However, since you are dealing with a huge number of the experimental conditions, and actually this is very interesting for the researchers to understand, shall we use the copper as an electrode, or shall we use other type of metal as an electrode? So so far the community majorly use gold, aluminium, are very typical metals. The reason is, once we replace other materials, the efficiency drop very significantly. So if it is convenience, or it is if you can access the data, it will be great if you can put the table of the exact power conversion efficiency in the appendix, because this will give a very good direction of the scientists to for comparisons, or to choose which approach or which combination of materials they can use for certain percent of the efficiency. So I think beyond the stability, the efficiency is also another interesting direction. So I would suggest, if it is possible, it will be great if you can put all this data in the appendix, rather than just show the normalized result. And then the last comment is, maybe you can share with us what will be your future plan in research based on your result achieved during the PhD study. So what are the ideas in the near futures? What kind of work you can continue further based on the current result? Thank you.
Okay, thank you very much for this question. According to what you said about providing the initial power conversion efficiencies, some of them, especially for compare different HTL materials, are already in appendix, and I believe in the edited version of thesis, I also added some information regarding other experiments in the text, not in the appendix. They are in the text, in the according parts. And what about my future work? According to what I presented now, there is a huge amount of possibilities what to do now. First of all is, as I mentioned, the best kind of material for charge transport material is polymeric one for improving the stability, and we have tough situation regarding the electron transport material, polymeric ones. So this probably, I hope, will be one of my topics. I actually plan to do it with my new student to try investigate different kinds of small molecules and polymeric materials which can be used as electron transport materials in order to improve the stability of the device. Not only electrochemical, but also photo stability and all other practical implementations. Another point which I wish to address probably in the future is to shift from this just basic research towards the trying to make something that can be commercialized probably in the future. So going from just getting the scientific results to getting something implementable. This is my hope for the future, just because I want to do something practical, probably. I hope this will lead to some results, but of course this will need to some additional experiments, additional investigations still. So a lot of research should be done in order to improve this. Other point that could be addressed regarding to this work, I already mentioned that I tested only metal electrodes in order to investigate electrochemical stability, but there are also different kinds of non-metallic electrodes like carbon nanotubes, like transparent electrodes, ITO, FTO, all other stuff. This also should be I also think I can investigate it. And another very interesting topic, actually all this work was concerned about electrochemical degradation under direct voltage. But in the work in solar cell, we also have this stuff called reverse voltage, especially in large modules. And when one part of the module of these interconnected solar cells gets shadowed, the reverse voltage appears quite frequently, and it also could lead to some degradation process inside the solar cell. So I think this topic about reverse voltage should be also addressed, and probably I would do this in future also.
Okay, excellent. Thank you very much.
Thank you for your questions.
Thank you very much, Professor. And now I'd like to ask the next jury member, and Professor Daniil Saranin, to ask any questions, and also importantly to say either you're satisfied or not with the changes in the papers.
First of all, many thanks for such complex and multidisciplinary work that was presented by Olga Yamilova. So, first of all, I would like to say that I satisfied with all changes and replies that was done by candidate. So no conflict in this part. So according to the speech and presentation of the results, I wanted to ask several questions about the following. So all of us are studying the thin film multi-layer devices, and so we could obtain the same XRD data, we could obtain the same IV performance, and for example, if we will compare the XRD data from our laboratory, from laboratory of Jovana, Olga, and Annie, all of them will show the approximately same XRD data, but the performance as well as stability, for example, with the same performance, could be really different. And one of the huge impact for the device stability is given by the nature of the charge defects, which have the serious impact for the charge collection efficiency, but for the stability as well, because plenty of them are mobile under applied electric field. They could accumulate at the interfaces and give impact for the corrosion processes at the heterojunctions and at the metal electrode as well. So the first question to Olga, could you give us several assumptions or could discuss what is your feeling about the major group of the defects that potentially could give negative impact to the interface stability of the devices, of the device configurations that were presented in your research? Many thanks.
Thank you for your questions. And regarding what is the major defects, major particles probably that's responsible for degradation, in my experience, in my opinion, this all regarding the organic part of perovskite material, because as far as I myself made a lot of different kind of perovskite materials, and sometimes, yes, we made the situation when at some point our lead iodide that was purchased from one company finished, and we opened another bottle of lead iodide from probably another company with another purity and all this kind of stuff, but the results remained almost the same. But when we made the same with a new bottle of some organic component like methylammonium iodine from medinium iodine, the results could change completely. So we needed to adjust new processing, new anti-solvent addition time, and all this kind of stuff. So probably this difference in the devices, of course, it's also connected to the hands of the experimentator, because even in the same laboratory from two different people you can get the different results even for the same configuration. But in my opinion, perovskite materials are just quite sensitive to all the kind of stuff that is around us, but still, in my experience, the major point here is some organic, some defects that can be in organic material, and probably this could be because of some synthesis process, because I don't know how is it for your laboratory, but we sometimes synthesize our own organic materials, and from synthesis to synthesis there can be some inclusions of initial reagents of this synthesis, of course, or some remainings of solvent, which is quite not so widespread, but still. But the main point is that there can be still some additions from the reagents of synthesis of these organic materials, which is not common for lead iodide. So all this kind of stuff will influence the stability and the efficiency of the device, in my opinion.
Okay, many thanks for your reply. I have another question, which is a continue of my previous one. So, could you make some conclusions and separate the state of the stability for the perovskite absorber film and device stability? So, for example, could you split the key things about the stability of perovskite thin films separately and its structural stability inside of the device? So, for example, you could easily obtain that the perovskite thin films inside of the device structure is a metastable stack. If you will investigate its optical properties or structural properties separately, so we will see clearly the degradation. However, inside of the device structure, we could see the opposite tendency. So could you make comments? Does the structural instability of perovskite thin films have key impact for the stability of the device performance, or it could be different?
Of course, I think it could be different, and actually not for my case, but my colleagues obtained the results that probably, for example, they tested different perovskite materials, and in terms of thin films, they had one rating of which is the most stable, which is the least stable, and then they tested them in the devices, and the rating was quite the opposite. So what was the worst, what had the worst stability in thin films demonstrated the best stability in complete devices. So in my major point of view, actually, if we talk about devices, the main part here is not how stable your perovskite material, but how it interacts with adjust layers, especially with these charge transport layers, because even if the material itself prone to some decomposition, if it's closed between these two layers, if these two layers don't react with with degradation products, and when they don't permit these degradation products to leave the device, so we can reach some kind of equilibrium probably at some point when these products of degradation converse somehow backward to the perovskite composition and stay in some kind of equilibrium. So I think the most important point is to find the right charge transport layers, electrodes, and all other stuff. But of course, the stability of the material itself will also influence the whole process, because, for example, methylammonium lead iodide is quite prone to degradation, because methylammonium is quite small cation, which can easily go through probably Fullerene derivatives. Because it's quite small. But if we change this small cation with a bigger one, with formidinium, with cesium, which are less mobile probably, and less concerned about not less concerned, which are less mobile, probably we could improve the situation quite a bit. But of course, the major part is to find a correct configuration for the device. I think with correct configuration of the device, even the methylammonium iodide-based solar cells can work quite well and quite long.
Okay, many thanks. And the final question from my side. About the nature of the possible defects. So what is your feeling? So you have a lot of data, a lot of device configuration, and the data set for the all charge transporting layers is really huge. So could you make some conclusions? What are the major requirements for the efficient passivator for the surface of the perovskite thin films? So maybe about functionalization, maybe about corrosion, anti-corrosion properties, so on and so forth. So according to the obtained results, where you have investigated the oxide, charge transporting layers, the different polymers, small molecules as well. So could you formulate the requirements for the charge transporting layer of the future? Thank you.
Yes, as I mentioned before, in my opinion, the ideal one is polymer material, because it forms, even if it's quite thin, it can form the very good quality film without any voids, probably, and will be chemically inert to the perovskite itself. And of course, if it forms quite good quality film, it won't let any products of perovskite degradation leave the device. So this is my major assumption. And of course, I also think that the good point is to have combinated charge transport layers, like having this polymeric thin film, and then have probably some kind of oxide, like it was for nickel oxide plus PTA system, because this kind of inorganic oxide material, they improve the whole device efficiency, the whole device characteristic, like improving the charge transport. They improve also the open circuit voltage, and as it was demonstrated in the table, the higher open circuit voltage will lead to the better electrochemical stability of the device and better efficiency, of course, it's connected. And from the other side, when we tried NIP configuration, the same good results were demonstrated if we used not only PTA as a top whole transport material, but PTA with the combination of vanadium oxide. So exactly the same situation. We have a polymeric material which separates perovskite and oxide, but this oxide is necessary to perform the better charge transportation in the device and perform a better characteristics, better open circuit voltage and better stability. But still, I think that layers that are adjust to the perovskite directly should be like polymeric, which are completely inert, processed with good compatible solvents, and form a film without voids. All other kind of materials like small molecules and even like nanolayers, which are with the thickness of one molecule, won't be quite good in this situation, in my opinion, because all of them will still have voids and will allow some volatile products of perovskite degradation to go outside and react with something else.
So I got the proper answers, so it means that's all from me. For the questions, again, Olga, many thanks for your huge research and nice results.
Thank you very much.
Thank you very much, Professor Saranin. And for now, the last questions from me. And actually, I already asked questions about Appendix A. Also, I'd like to say that I'm fully satisfied with the answers or changes made in the thesis by Olga Yamilova. Now, I just would like, it's my curiosity to understand better slide 16. 16. Elena, slide 16, 16 from presentation, yeah.
It's not my presentation.
Okay, I can ask on that slide, yeah. Okay,
16. This one, yes.
Yeah, that one, yeah. So I try to understand the process. No, please keep the slide, yeah. Okay, yeah. Okay, as I remember, so you found that methylammonium cation after 1 volt, yeah, applying. So this cation migrates to both to PCBM side and also to P.PSS side, yeah.
Yes.
And you know that perovskite materials, they can exhibit cation conductivity, yeah. So it means if the cation is removed, so it should be, the rest of the framework should be negatively charged. No, cation is positively charged, yeah? And positive charge is migrating on both sides, up and down. While lead and iodide, as I remember, they do not migrate significantly. You showed in your thesis. So, and how you can explain me the process which will take place here? Because definitely negatively charged framework is not stable. You say it should be oxidized. What happened here?
According to our assumption, so migration of methylammonium cation into PCBM is just a simple migration under the electric field, of course.
Okay.
Yes.
And it's reduced. Methylammonium is reduced and gaseous.
You mean in the PCBM layer, or?
Yeah.
I'm not quite sure about that, because TOF seems doesn't provide us with information either was this kind of cation reduced or not.
Okay.
And if we talk about migration into P.PSS layer, so it can't be because of applied electric field, because it would be strange if our positive charge would migrate to the positive electrode. So the only explanation that we have that inside the perovskite layer, we have this redox process, which was mentioned in the mechanism. So we had some kind of formation of methylamine, and this methylamine reacted with polystyrene sulfonic acid, and thus it migrated in the form of a volatile which reacts with the acid. It migrated into the P.PSS. But if we have a redox process, so probably at the same time we had an opposite kind of process inside the perovskite film, and so this somehow probably compensated this negative charging that you mentioned, most likely. So probably we had some formation of molecular iodine, and this molecular iodine, actually, as I remember in the thesis, there was a figure when for this part, this iodine also migrated in a molecular form, as I suppose, to the top silver electrode.
Yeah, but you showed that, as I remember, lead at iodine practically does not change their positions.
Yeah, lead hasn't changed its position completely. Iodine migrated still to the top electrode, which was demonstrated in the thesis, and the most drastic changes were for this kind of cation, but still, I don't think that the concentration of the amount of migrated cations was too much to induce some significant process inside the perovskite film. As you can see, the concentration of the intensity of methylammonia cation inside the perovskite area is still pretty high. So the major of them still remained in the film in some form. So probably the charging which you mentioned was not so high to induce some additional process. But of course, it should be mentioned that this results for TOF for BEST for 1 volt 300 hours devices. These devices are completely dead. So their efficiency at this point was almost zero. So, of course, there probably could be some additional process at this point, which led to the complete degradation of the device. So this device already isn't working. So this means this perovskite is already unable to perform its duty in order to absorb the sunlight and convert it into the energy. Converted into the ion splitting.
Okay, thank you very much, Olga. And I already said that I'm satisfied by the changes. And now I'd like to ask, do we have audience, any people? And I'd like to ask if anybody would like to ask questions to Olga. Because I cannot say how many. Oh yeah, it's a lot of, yeah. Okay, I ask a question. If anybody would like to ask Olga any questions, you can send a message. and I will allow. But now I would like to ask the supervisor, Professor Keith Stevenson, to say a few words about not the thesis, but about the applicant, about Olga Yamilova. Please, Keith.
Thank you. Can everyone hear me all right?
Yeah, very good.
Okay. Well, first of all, I'd like to thank the jury and the chair for assisting Olga in the defense of her PhD thesis at Skoltech. I know you've read through a lot of interesting studies and materials in this particular area, which turn out to be extremely complex and reactive in a sense. And I would say that over the course of her study, one of the first papers that Olga published was having to do with looking at the TOF-SIMS phase segregation in the context of the device architecture. And this is where things got extremely interesting just from looking at the base methyl ammonium lead iodide system, MAPI for short. And then, of course, in parallel, several of our colleagues were starting to explore many other compositions that seemingly would uphold the same perovskite structure. But as you know, that this is not so simple to study, even from simple things like X-ray diffraction, because these are in the thin film limit, and X-ray diffraction is not that sensitive unless you're doing very high grazing angle type studies or using other types of synchrotron-based sources to study the very intimacies of this. But nonetheless, there was a lot of careful thought put into how to at least benchmark on a relative sense these different combinations, different materials, and particularly the active materials. And it was, as discussed, this excess stoichiometry of the halides is not so trivial. But what she found, along with her other colleagues, is that it's very sensitive to the stoichiometric ratio, and this likely drives some type of both kinetics but thermodynamic equilibriums that go back and forth depending on the redox process. So in general, the main contribution was to show that this is in fact electrochemistry, which is not always so obvious to a lot of engineers and physicists working in the field. But the fact is, as quite remains, is that an analytical chemist knows that the iodine, iodide, and also the lead can be extremely redox active, even in the solid state sense. And so the complexity here is much more advanced than what you would see in kind of, say, single crystalline silicon or amorphous silicon, where you're talking about difference between the crystalline regions and the grain boundaries and so forth. Here it's very complicated. And one thing that Olga didn't elaborate on is that we've done lots of different studies, including photo-induced AFM imaging to look at large-scale photo-induced chemical phase segregation. It's quite rapid and fast and very confined in the nano-length scale, which certain other characterization techniques do not pick up upon. But I would say that really in an independent fashion, Olga advanced again with this idea of using chemical imaging, in particular TOF-SIMS imaging, which has been highly important contribution in the field as a whole. One of the things that we've tried to focus on, as well as others involved in this area of research, is the need for more careful benchmarking studies, as was mentioned by others. The suggestion to include in the appendix all of the raw data is somewhat hard to index and even compare on a case-by-case or apples-to-apples basis. As we know, it's one of the things that in particular has limited organic photovoltaic research, but also now the perovskite photovoltaic research. But I would say that at Skoltech, there's a lot of know-how that isn't necessarily published because it takes a lot of diligence to run through many, many different sets of experiments and statistically compiled data. So you notice that there are error bars on really most of all of the data sets, which means that there's hundreds, if not hundreds of thousands of experiments being done by the Skoltech group, in addition to paying close due diligence to the literature, which is rapidly moving at a very fast pace, and oftentimes it's very difficult to keep your head on top of what others are reporting, and then the fact that they can't necessarily, one study cannot be compared to another complicates the matter. But nonetheless, she was not intimidated by this challenge, and she hopes to continue in this line of research at Skoltech. And I think she's well equipped, well trained, and much to her persistence and her careful, detailed analysis, she's been able to provide significant impact to this field, albeit it's still somewhat empirical. But there is a lot more chemical understanding of these systems than has been reported prior to Olga and some of the other Skoltech colleagues involved in this line of research. So I'm extremely proud to see her growth and development, and the fact that she could leverage so much capabilities and for the sake of Skoltech, but also for the global science in this particular very important emerging area of solar perovskite-based solar cells.
Thank you very much, Kees. And again, I'd like to ask our audience if any questions appeared. And anybody would like to ask questions, please notify somehow. Ilona, there is no, yeah?
No, I can't see any questions.
Okay, thank you very much. Yeah, and now we have a closed session, and I'd like Elena to provide this closed session, because we will discuss about the final result. Okay, I'd like to
please use the microphone, or the Olga's one on this one.
Yeah, I understand. Yeah. Okay. All 5 members of the jury voted, and finally we have such results. The final results are the following: that final decision is that thesis is pass, but minor revisions required. So the candidate thesis is accepted, subject to minor revisions, without the candidate being required to receive the PhD thesis defense. There were several important or minor changes should be done in the thesis text, but in general, all jury members voted that Olga Yamilova should be awarded the PhD degree of Skoltech. So that's the final decision.
Thank you very much.
Congratulate, yeah, Olga.
Thank you very much for all my jury members that you accepted to be my jury members. Actually, thank you for all your questions, for all your suggestions during the review part. Also, big thanks to my supervisor, Kit Stevenson, for all this help during this work. Thank you for the whole Skoltech workers who helped to organize all this process. I will continue my research. I'm sure about it. So I wish for me and for you many more interesting results, interesting probably collaborations in future in some various points. And yes, thank you once more for every one of you.